In this video, we start the second part of the electrical conversion chapter that is about DC to AC inverters. The second part is subdivided as follows. In this video, after an introduction on solar inverters, we will see the main characteristics of this device. Then, in the next video, we are going to talk about installation concepts and the different topologies that you might encounter when you want to put together different PV panels in a PV system. Thirdly, we will see the basic implementation of DC to AC conversion. In reality, every inverter brand has its own proprietary topology, so it is virtually impossible to go through all the different nuances of a DC to AC inverter embodiment. However, in general, there are always an H-bridge along with a control algorithm to modulate the output signal. For this purpose, usually pulse width modulation is used. Then, in the lecture about the overall configurations, we ideally open an inverter and we see what are the different parts involved. And in another video, grounding-related issues which can arise when connecting the PV modules to the inverter are treated. Finally, we conclude this series of videos discussing the efficiency of the inverter in order to be able to calculate the overall energy yield of a PV system throughout the entire year. Coming back to this slide that summarizes the most important components forming a PV system, we can find the inverter again in the balance of the system block. It is very important to note that the term inverter can have two different meanings. First, it is used for the actual inverter, which is the electronic device that performs the DC to AC inversion, as we are going to see. Secondly, the term inverter is also used for the total unit produced by manufacturers, and thus, depending on the application, it may contain an MPP tracker, a DC-DC converter, and a DC-AC inverter. In grid-connected systems, the inverter is connected directly to the PV array and converts the DC electricity coming from the PV array into AC electricity. Besides, such an inverter usually contains an MPPT system. As such an inverter is connected to the electric grid, it must also be synchronized with the grid, meaning that the phase angle of the AC signal coming from the inverter must be equal to that of the grid. In order to increase power quality of the grid, the injected signal should have a minimal harmonic content. Let's now see the main characteristics of a solar inverter, intended as the power electronic device that actually performs the conversion from direct current to alternate current. In general, an ideal solar inverter should fulfill the following requirements. First, it should be highly efficient because the owner of the solar system wants to maximize the utilization of the DC electricity generated by the PV modules when delivering it to the grid or to the AC loads. To meet this goal, we seek for solutions that can ensure low losses. Sometimes special demands about grounding need to be met. We will come back to this aspect at the end of this series of videos when we will talk about the potential induced degradation. Some additional circuitry is often included to make sure that if any high-frequency harmonics are traveling along the cables, they will neither go towards the PV modules nor to the grid. This requirement is enforced by law in most countries, since the harmonic limits of both sources and loads connected to the grid are regulated. Special requirements exist also for electromagnetic interference, which is regulated by law in most countries. The goal is to minimize the unwanted influence of electromagnetic interference on other equipment in the vicinity of or connected to the same supply. Then, in many instances, the PV system needs to be installed outdoors, and the inverters should meet certain specifications regarding temperature and humidity conditions. Of course, more expensive solutions exist in case of inverters that have more stringent capability against dust or outdoor operation. The embodiment is usually classified according to the IP standard, which rates the degree of protection provided against intrusion. IP45 means that dust do not enter in a sufficient quantity to interfere with the satisfactory operation of the equipment. In particular, the second digit 5 indicates the level of protection against water jets coming from any direction. Usually, the device has to be designed for high ambient temperatures and 20 years of operation, although most of the time brands offer warranties ranging around 15 years. Nowadays, these components are becoming more and more reliable, but power electronics and batteries remain the most fragile part when it comes to maintenance, while PV panels are usually the sturdiest part of the PV system. Last aspect to take into account is a silent operation, so no audible noise. Often for inverters, when a loud clicking noise can be heard, it might be a signal of malfunctioning of the chopping section. When designing a PV system, a crucial part is the choice of the inverter. In particular, apart from all the aspects we have mentioned so far, the choice between a single-phase inverter and a tri-phase inverter is really important. A household is normally served by single-phase AC power, so this is the best choice for low-power systems and in general for standalone applications. If the photovoltaic system is connected to the grid, the single-phase option can still be considered. Issues arise when the power injected into only one phase is too high. In this case, one of the phases would carry too much current, causing an imbalance in the system which compromises the stability of the grid. Generally, a tri-phase inverter is instead used when a 5 kilowatt peak threshold is reached. In this case, the current will be directly balanced throughout all the phases. We will see more in depth the two topologies of inverters in the next videos. As already mentioned, the word inverter might refer either to the DC-AC converter or to the power electronic unit that includes many other things inside. So for example, we have the MPP tracker, the DC-DC converter, the DC-AC converter, and some models even include a battery charge controller in it. In an inverter, DC power is transformed into AC power. Generally, the DC input voltage of the inverter must be constant. However, the maximum power point voltage of the modules is not. Therefore, a DC-DC conversion stage is used to transform the variable voltage from the panels into the constant voltage required by the DC-AC inverter. While the constant output voltage is achieved by means of a feedback loop, the desired operating point of the PV array determined by the MPPT algorithm is used to control the duty cycle of the converter. Finally, the topology that includes a battery charge controller is typically used in the standalone applications, which include a battery system eventually connected to AC loads. In this case, all these components are fully integrated in the inverter. Let's now recap what we have seen in this video. First of all, the inverter belongs to that part of the PV system which is called the balance of system, or BOS. Then we went through the main characteristics that every inverter show. Also, we saw that depending on the size of the system and the application, a choice has to be made between a single-phase and tri-phase inverter. Finally, we clarified that the word inverter can refer either to the power conversion section that modifies the signal from DC to AC, or to the overall power electronic device that includes also other components. In the next video, we are going to see how the inverter is used in different types of PV systems configuration.